So in this class, I want to give you some important theorems uh, corresponding to the Markov chain. So first of all, I want to give the theorem of Chapman and Kolmogorov. So Chapman, Kolmogorov. Yeah. What is this theorem says? The theorem says that if capital P is the TPM of a homogeneous Markov chain, then the n step TPM P of bracketed n. So P of bracketed n means the transition probability at n step. Transition probability at n step is equal to the product of the transition matrix n time. This P to the power n means product of this means P into P into P and so on so n times. That means the transition probability at n step denoted by P to the power bracketed n is equal to n time product of the transition probability matrix in one step. So n time products of the one step transition probability matrix. That means if I have a probability transition matrix P as 0, 1, 0, 0, say here I am having 0 0.3, 0, 0.7 as I have constructed before, and then 0, and I will have 0 0.3, 0, 0 point, so 0, 0, and then 0 0.7, and then 0, 0, 1, 0. So if this is my transition probability, then the transition probability second step, after second step will be nothing but P into P. Similarly, the transition probability after third step will be P into P into P, and I can say P to the power 3 time product of the one step transition matrix is equivalent to the transition probability matrix in third step. Okay. Similarly, the transition probability matrix at n step is equal to P into P into P n step. So this is one of the important theorem of the Markov chain, and it is given by Kolmogorov. It is given by Kolmogorov. Now I would like to give some more theorem. Before that, I will give one definition under which condition a TPM is a regular matrix. A TPM is a regular, already we know that it is a stochastic matrix, but under which condition it will be a regular matrix. So regular matrix, under which condition we say the TPM is a regular matrix. A stochastic matrix P, a stochastic matrix P is said to be regular regular matrix, regular matrix if all the entries, if all the entries of p to the power m for some positive integer m, for some positive integer m are positive, are positive. That means, suppose here I am having the TPMS. So like this, I am having 0, 1, 0, 0, and so I have 0.3, 0, 0.7, 0, and I will have here 0, 0.3, 0, and 0.7, and then 0, 0, 1, 0. So this is my TPM already I constructed. Now here you see that here it is P1. It is P1, one step transition probability. Now here you see that some positions are there in this TPM where the entries are not positive. Not positive in the sense they are 0. They are 0. But if I find P square, okay, if I find P square and I found that some of element in the 0 position are non-zero but they are positive. Okay, so similarly I will find P3 and so on, so I will find PM. After finding PM, I will have another transition probability matrix. In the transition matrix, if all the entries are positive, means suppose in the P square this becomes something non-zero, this becomes something non-zero, but this is 0. So next I will find P3. In the P3, suppose I got this is non-zero, this is non-zero, but this is 0. Then I will go for P4. And P4 I got this is non-zero and this element is also non-zero, but these three elements are 0. Then I will go for P4, P5. P5 if I get all the elements are non-zero. All the elements are non-zero. Then I say the TPM is regular, because here I am saying that the stochastic matrix P is said to be regular matrix if all the entries of P to the power m for some m, for some m, not all m, for some m. That means it may be P1, P2, P3, P4. No need to go for any m number of time. If P4 is giving each entry of the original TPMS non-zero entry, then we can conclude that the TPM is regular. The TPM is regular. For that, we have to check the uh, element in each position, and we will see that originally it was non-zero, so further we no need to check it, it will be non-zero. Then whatever position is with 0 element, just I will find p square p3 and I will check whether those 0 elements are converting to non-zero elements. Okay, after some times, after some product p1 p2 p3 p4, we will find that these non-zero elements will become these 0 elements will become non-zero. Then if I get all the 0 elements as non-zero after some product, then only I can say whatever TPM I am having, that TPM is regular. Otherwise, it is irregular. Otherwise, it is irregular. Okay. So this is the one of the important concept we are going to use while solving the problem. Here I would like to give one note also. The note is a homogeneous Markov chain is said to be regular A this is the normal definition of regular matrix. A homogeneous Markov chain is said to be regular, if its TPM is regular. If its TPM is regular. If its TPM is regular. If the TPM of a Markov chain, a homogeneous Markov chain is regular, then we can say that the homogeneous Markov chain is also regular. So depending upon the TPM, nature of TPM, we can able to decide the nature of the homogeneous Markov chain. So there are three other theorems I want to state here and try to explain you. Theorem 1, proof is not needed. What is the theorem 1? If P, small p, which is nothing but Pi, that means only row will be there. There is no column, only one column. Okay. If the state probability is the state probability distribution distribution of the process at an arbitrary time, at an arbitrary time arbitrary time then then after one step after one step after one step it is after one step it is small p into capital P, where capital P is nothing but ppm of the chain, where capital P is the ppm of the chain. Okay. And after n step it will be p to the power p into p to the power n. So what is the meaning of this one is, if I am having a TPM capital P and one probability distribution, state probability distribution Pi, okay, then the transition probability, the probability distribution after first step will be nothing but P into capital P. That will be the probability distribution, state probability distribution after one step. Similarly, the state probability distribution after n step will be small p into p to the power n. So p to the power n means the transition probability at n step. So if I multiply the probability distribution p with n step transition probability after n step, then we can have the state probability distribution at n step. N step. So this is the first theorem. This is the first theorem. And the second theorem is, next theorem is, theorem 2 is, if the homogeneous Markov chain is regular, if the homogeneous Markov chain chain is regular, then every sequence of state probability distribution, then every sequence of state probability distribution approaches a unique fixed probability distribution. Approaches chase a unique fixed probability distribution. That means if a homogeneous Markov chain is regular, then every sequence of state probability distribution, that means P into P, P into P square, P into PQ, and P into P to the power n approaches to a fixed probability distribution. Okay, and that is called the stationary state distribution or steady state distribution, which is called the stationary for the stationary state probability distribution or steady state distribution. Steady state distribution. Okay, so if it is approaching to a fixed probability distribution, it is called steady state probability distribution. That is limit n tends to infinity p to the power n will be nothing but pi. Where the state probability distribution at step n, where the state probability distribution at step n at step n, that is Pn is equal to P1n, P2n, and so on, so Pkn. Okay, so if this is state probability distribution, then if n tends to infinity approaches to a fixed probability distribution where pi is nothing but pi 1, pi 2, and so on, so pi, and so on, so pi. So this is another theorem. It happens for the homogeneous Markov chain. Okay, and the next theorem, theorem 3 is if P is a TPM, of of the regular chain, then at the long run, small p into capital P will be always a steady state probability distribution is equal to pi. So this pi depends upon the state probability distribution small p. So these are the theorems we will use when we will solve the problem.